So let's start our review of Chapter 6 material. This revolved all around these substitution and elimination reactions. All right. So the first thing I get to ask you is just what is the mechanism that produces the major products for each of these reactions? But really what I want you guys to do is flip to a new page in your notes. All right, I want you guys to try to fill out this chart as best you can from memory with what the reactions are going, what the mechanisms are in each one of these categories. That's essentially what that question is asking, and that's kind of the most basic thing that we need to be able to do. Remember, you're going to be given this list of bases and nucleophiles, but you need to know what happens to each one of these substrates, right? So if we can fill in this chart here, we're good to go. That's like our starting point. So take a second and see if you can't fill in this chart from memory. Obviously, we all know where to look in our notes to find it, but can you do it off the top of your head? All right, so to start it off, we're trying to fill in this chart as best we can from memory. All right, again, you'll be given this part. All right, it's this part down here that you want to make sure you can do. All right, so how am I going to do this? So like kind of reason our way through this real quick. Let's start with this first one. These are strong bases but bad nucleophiles. So that means they're going to prefer what? Substitution or elimination? Elimination for the bases. The bases are elimination. So if you're a strong base but a crappy nucleophile, everything in this category here is going to be elimination, all right? These are all E2. I'll tell you what, I don't care if you know whether it's E1 or E2. You just got to tell me elimination, all right? For our purposes, they produce the same products. Likewise, similar logic. We're going to skip over this one for a second. In this third category, these ones are weak bases but strong nucleophiles. So what are they going to prefer, substitution or elimination? Substitution. All right, so everything in that category is substitution. But here we got to know the difference between the primary, secondary, and tertiary, because these mechanisms do impact what our product is. Okay, SN2 are what are undergone by primary and secondary, and SN1 are our tertiary. Okay, so again, reasoning through this, these are our bases that are crappy nucleophiles, so they are all elimination. These are our nucleophiles that are crappy bases, so they are all substitution. Let me get a better color. Okay, so those two categories are kind of the easiest to fill in there because everything's the same. This one right here is probably the hardest, so let's do that one at the end. These weak base, weak nucleophiles, right? So these are things that are bad at both. Because they're bad at both, they don't react with primary or secondary substrates at all. Okay? But for our tertiary ones, our tertiary are the most reactive out of all of them. So even though these are crappy nucleophiles and crappy bases, they still react with our tertiary substrates. And you get a mixture of SN1 and elimination. This is the only category where you have both of them in there. All right? Our strong base, strong nucleophile category is also, so each one is going to be a little bit different. The primary will favor substitution. That primary carbon is really accessible to that nucleophile, so it favors substitution. Secondary and tertiary, that electrophilic carbon's more hidden. It's harder to get to. So because of that, the base part of this takes over, and these ones favor elimination reactions. All right, so this is the chart that we want to be able to fill in. And again, when you get done, sort of color coded here, you should have like this little bit of a staircase thing going on, right? That we can sort of see our dividing line. Okay, and then this one's the oddball, the mixture. Yeah, Tetris blocks, whatever works, right? Be able to take a step back and kind of see that, okay, on one half I have my elimination, and on the other half I have my substitution. Kind of just, again, sort of helps you figure out whether you filled it in correctly. So that's what we want to do. So then, like, if we can do this, if we can fill in this chart from memory, then we can definitely go and answer these types of problems here, right? Because then we're just playing the game where we're finding out what box each of these satisfy. So for this one here, my substrate would be what? Primary, secondary, or tertiary? So this one's primary. What did I tell you to do when you see Na, sodium? We're going to erase it and replace it with a minus sign. Okay, so this is a primary, and this one here would fall under the category of strong base, strong nucleophile. All right, so then if I could fill in that chart, then I could just easily use it to figure out that this one would be an SN2 mechanism. Okay, so that's definitely what I would be doing when I was studying, is I would take one of these charts, I would erase everything, and then I would try to fill it in from memory here. Because again, you're going to be given this part up top, right? You need to be able to do this part down here. All right, so just practice creating one of those things on your own, and then you'll be able to use it throughout the exam. All right, so for this one, now this one is a secondary. Again, when we see sodium, we're just going to get rid of it. Replace it with the minus sign. But now our secondary substrates will react with strong bases, strong nucleophiles in elimination reactions. So it's E2, but again, I'll let you just put elimination. All right, so again, we have to be able to distinguish between SN1 and SN2. For E1 and E2, for our purposes, they give us the same product, so you can just tell me it's an elimination. Okay. All right, and then the last one here, is this primary, secondary, or tertiary? Okay, so I know this is like, there's a lot of crowding going on here, but let's convince ourselves that this is still just a secondary substrate. Because again, all I'm doing is looking at the carbon at the base of that chlorine, at the base of that leaving group, and counting how many neighbors it has, how many carbon-carbon neighbors it has. So 1 and 2, right? These ones over here don't count towards what I'm just determining primary, secondary, tertiary. So this is, again, a secondary substrate. And then what the heck is this thing here? All right, let's take a second to copy down this product and then this substrate rather. And then I'm going to go back to that list of bases and nucleophiles, and we're going to see if we can't spy this thing. I guess I can just copy it. It's too big. All right, give me a second. Okay, so again, we see sodium. We're going to just erase it and put a minus sign in there. But then we got to try to find this thing here on our list of bases and nucleophiles. So everybody take a second and see if you can't spy where that thing is on our list. What category is it? So this is a weak base and a strong nucleophile. This corresponds to this right here, COO minus. Right? Again, that R means anything. This C, let me just. So RCOO minus is code for something attached to a carbon that's double bonded to one oxygen and then single bonded to an oxygen with a negative charge. These are the same thing. This is like the shorthand code for this right here. Okay. It's probably the funkiest looking of all the ones on here, for sure. Okay, and importantly, if we're going to do our reaction, it's going to be this oxygen that replaces that leaving group. That's going to be where my new bond is between that oxygen and my electrophilic carbon. In this case, in this particular problem, I was just asking you to tell me what the reaction mechanism is. So in this case, we have a secondary with a weak base, strong nucleophile. So this would be an SN2 reaction. All right, in this category here. What's up?
Can we would we have to draw the product as well?
So we're going to see the different types of questions that I can ask. I can ask you just what the mechanism is, right? Basically, can you fill in this chart correctly? But absolutely, there's going to be other questions that are going to ask you to draw the product as well. Yeah. Which we will do now. So again, these are SN2. Okay, so step one, again, basically, can you fill in that chart correctly and read it correctly? All right. Now, absolutely, now we're going to go on to practice drawing products. when we fill in this chart, one thing I just want to clarify, when we fill in this chart, these are the major products of those particular reactions, right? The major products when you combine a primary substrate with a weak base strong nucleophile is SN2, right? That's what we use this chart for, is to figure out the major product. But these two are always in competition with one another, elimination and substitution. You always get a mixture of both. This chart just tells you which one's the major product. Okay? But for each reaction, I can ask you specifically what is the substitution product and what is the elimination product. Okay, so we want to be able to draw substitution products and elimination products, right? So that's what we're going to do first. And then the last question on here will just be, what's the major product? Draw me the major product. So where you're going to combine your skills of both drawing products and being able to read that chart correctly. But for now, we're just going to make sure that we can draw substitution products and draw elimination products.
What day is our exam again?
Friday. All right, so let's go through these. Again, at first I'm specifically asking you for the substitution product, right? Regardless of whether it's the major product or the minor product, I want to see that substitution product. So what happens in these substitution reactions, we have a leaving group that's going to be swapping places, right? So we see sodium, we're going to get rid of it and replace it with a minus sign. A leaving group that's swapping places with my nucleophile, right? That's what these substitution reactions are doing. So my product here will still have these 1, 2, 3, 4 carbons, all right? But then I'm going to replace that leaving group with that nucleophile, substitute it out. All right, so for this next reaction, again, I'm going to get rid of sodium, just replace it with a minus sign. I'm again going to be replacing my leaving group with my nucleophile, but of course now my nucleophile is this big ugly thing here. Okay, and importantly, I have my leaving group on this wedged bond here. So I got to know whether or not I'm supposed to invert my stereochemistry. Remember that primary and secondary, because they undergo SN2, that means we got to invert our stereochemistry. Meaning if it was a wedge on my original structure, it's going to be a dash on the product, or vice versa. If it was tertiary, it would be SN1, and I got to draw both the wedge and the dash. Okay, so I'm going to invert my stereochemistry. I'm going to change this to a dash. I'm going to run out of room for sure. Okay, and I got to attach my nucleophile here, and specifically just like in the example above, right? It was a new bond between carbon and oxygen that was formed. That's how I got my new functional group on there. It's going to be the same thing here. I'm going to have a new bond between my carbon that was at the base of my leaving group and the oxygen in my nucleophile. But now there's a bunch of junk on the back end too, and I have to make sure to include that. Right? So we can count carbons. I'm going to have my oxygen attached. Okay, that's this purple one here. That oxygen is bound to a carbon. So I'm going to put that in there. That carbon has a double bond to another oxygen. And I'm going to make sure to include all 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons on the back end there. This is really ugly. I got to clean that up. Okay, so this is by far the worst looking nucleophile because it's big and ugly, right? So let's just make sure that we can see how it's attached. I'm going to color my carbons. Right, again, I have this one that's at the base of that oxygen double bond. Whoops. This one, etc. Right? So you want to see how that whole nucleophile, it's like I pick up that whole nucleophile and attach it onto the other end. Okay. One thing that I know stumps some people is, let's say that there was another sort of wedged bond over here. That does not get inverted. It's only the ones on the carbon with the leaving group. Right? There's nothing happening at this carbon at all. So if it's a dash or a wedge or whatever, it doesn't get touched. It just stays the same. It's only at that carbon with the leaving group that you're going to switch it. Okay. And then for this last example, how many products am I going to have? I'm going to have to draw both because this is a tertiary substrate. So it's going to undergo the SN1 type. So you got to have both a dash and a wedge. All right. And again, this one, I picked it because it's kind of an ugly one. Let me just sort of show you what one of these looks like real quick, and then we'll talk about it. Okay, so I gotta draw my other product, but before we get there, before I ugly this up even more, let's just convince ourselves that this makes sense here. I started out with just the same carbons that I had in my original substrate. Okay, and then I've added on my nucleophile here. Importantly, because I started out with this neutral nucleophile, it lost that hydrogen. All right, so when my nucleophile attaches, I lose that hydrogen because it starts off as a neutral nucleophile. Okay, just to kind of remind everybody, we sort of made this chart here that whether you're using the hydroxide or water, you're going to get an OH group on there. Both of those will give you the same thing. Again, if you start out with one of these neutral ones, you'll lose a hydrogen. All right, so likewise, I started out with this alcohol here. That'll attach itself as our, in this case, 2 carbons, right? It loses that hydrogen. Same product as if I were to start out without that hydrogen. Okay, so either one of these will give you the same substitution product. All right, but then I'm not done. I gotta go in and also make sure to draw my other product as well. And to do that, I'm just going to flip the wedges and the dashes. All right, so I'm gonna turn this one from a wedge to a dash, and this one's gonna go from being a dash to a wedge. If you flip the side that dash and wedge was on as well, it doesn't really matter. As long as your nucleophile is on one wedge bond in one structure and the dash bond in the other structure. What side you put them on doesn't matter. Okay? So these would be my 2 substitution products for this reaction. Getting all sorts of ugly. Again, I gotta draw both, because I started out with this tertiary substrate. Okay, so now we have these specifically asking to draw the elimination products here. So what's my functional group going to be in my elimination product? Alkenes. I'm drawing alkenes in this particular section, right? And we got one rule for what alkene would form. And what's that? Does anybody remember? So we're going to get the most highly substituted alkene. Okay? Let's actually do this one first because it's a little bit more straightforward. So I'm going to look at I'm going to draw an alkene. I know I'm going to have to put a double bond in, right? I'm going to have to include this carbon at the base of my leaving group in the double bond. It can't be like over here or something like that, right? It's always going to have that electrophilic carbon involved. So I'm going to have, start out drawing all the carbons that I'm given in my substrate, and I know that the double bond has to be on that carbon there. So I got 2 choices. I can either draw it in this direction here or in this direction here. Wow, that was crazy. Okay, those are my 2 possibilities here, because again, it has to involve that electrophile, that carbon that was at the base of that leaving group. And then which one we pick is, again, the whole logic is we're going to pick the more highly substituted alkene. Right? So this one is not going to be it. It's going to be that one because my alkene is more highly substituted. Everybody knows what I mean by that? More carbon-carbon neighbors, right? So in order to determine which one's more highly substituted, I'm going to look at each carbon on either side and then count 1, 2, 3 versus just 1 over here. That's how I determine which one's more highly substituted. All right, so again, going back to this first one, again, I know it's going to be between, on that carbon there. So again, I have these two options. It's going to be either on this side or on this side. Which one am I going to pick? Yeah, in this case, they're equivalent, right? So I'd have to draw them both. These are two different products that I would get. Neither one of them is more highly substituted than the other one, so they're equally favored. So in this case, I have this mixture here of both of these.
You have to draw one.
Yep. Right, because they're two different molecules, right? This one, how many? 1, 2, 3, 4, 5, 6. This one's 2-hexene, and this one's 3-hexene. Those are two different molecules that are equally favored.
Oh, okay.
All right, and then for this last one, I'm again looking for elimination product. So I'm going to sort of start off. I know that this carbon right here has to be involved. So I'm going to draw. I got these two possibilities. It's either going to be here or here. Right? Because again, it's got to involve that carbon, that electrophilic carbon that was at the base of my leaving group. So then which one of these is going to be my preferred product, the left or the right? Right, again, the more highly substituted one is this one here. So this is my elimination product. Right, so elimination product, you're drawing these alkenes, and again, you're always going to pick the more highly substituted alkene. One problem that I know was throwing people off in the homework was very similar to what I just did. Right, so what I just did was this. Again, my elimination product was this, okay? But now, if instead of just being a cyclohexane ring, it was a benzene ring, okay, when I draw my product, this is incorrect. Why is that product incorrect? What's wrong with that? A lot of answers, right? So, okay. So, the key here is let's look at this carbon right here. There's something very wrong with that particular carbon. How many bonds does it have? 5. Carbon with 5 bonds should make your organic chemistry brains explode. Carbon can never have 5 bonds, right? So I know that this is really tempting to draw because you're like, I'm going to put it on that more highly substituted carbon. But we got to remember like our basic rules of drawing structures. Carbon can't have 5 bonds. So this product right here cannot possibly form, which is why it forms on the other side instead. Okay? So these are very, very similar, but again, the whole difference here is that this carbon can't have 5 bonds, right? And because that was a benzene ring, it started out with that extra double bond. Cool. All right. So now we're going to put everything together. We're going to have to use both our chart and our skills of drawing products to determine the major product of each of these reactions. Let me finish filling out with some examples. so let's take a second to copy these three down, and then I'll switch it back to that bases page so we can sort of look up our nucleophile bases here. I'm going to switch it. Everybody's got it? All right, so now let's go back to this page here. So get rid of these markings. Everybody take a second and try to answer those questions. All right, so let's go through these. Now this is kind of combining everything together, right? Our skills of drawing the products as well as being able to use that chart to predict what the major product is. Okay, so here I would have to go through classify my substrate. In this case, it's a secondary substrate. And then this SH2, which category did that fall in? This would have been a weak base, but a strong nucleophile. So using my chart, I'd be able to see that this would be an SN2 reaction. All right, I need these two pieces of information, and then I can use my chart. So because it's SN2, I'm only going to have the one product, but I'm going to have to make sure to invert that stereochemistry. And in this case, my nucleophile, again, it's neutral, right? So I got to lose that hydrogen when it gets attached. So we can update that little list that we built here. Similar to how water and the hydroxide ion both attach as an OH group. Will attach as RSH. Right? So if you start out with a neutral nucleophile, it's going to lose a hydrogen. All right, so that would be my product there. All right, so now I'm going to play the same game here. I'm going to classify my substrate as primary, secondary, or tertiary.
Secondary.
Again, in this case, it's also secondary. But then what category does this reagent fall in? So this is a strong, right? It's both a strong base and a strong nucleophile. Right, I'm going to erase my Na, put that minus sign there. Okay, we can go back to our chart here. NH2 with the minus sign. Anytime you see nitrogen with that minus sign, that falls in that category here. R means it doesn't matter what's on the other end. It could be hydrogens, or it could be, you know, 2 CH3s. That was very ugly, but hopefully you get my gist. Right, whatever it is, that oxygen with, or that nitrogen with the minus sign. Notice that in this category here, a lot of these are nitrogen with the minus sign, or when you have oxygen with the minus sign. All right, those are all kind of quintessential strong bases, strong nucleophiles. So in the case of secondary, these actually prefer elimination reactions. So what I should have drawn over here was not the substitution product, but this is going to be the elimination product. Okay. And then for my last one here, this is a tertiary substrate, and water falls into what category? This one's weak. Weak base and a weak nucleophile, which in the case of a tertiary means we're going to get a mix of SN1 and E1. Both of those are, you know, again, this is all about predicting the major products. It turns out with a tertiary and a weak base, weak nucleophile, you get substitution and elimination that happens equally. So I got to draw both of them. There are no dashes or wedges here, so I don't have to worry about that, right? If there were dashes and wedges, I would have to worry about my SN1 and drawing both of them. If you don't see dashes or wedges, you just don't have to worry about it, right? So I'm going to do my substitution. Again, this is neutral, so it's losing that hydrogen when it gets attached. And then my elimination product is again that alkene. And just real quick, you want to convince yourself that these are all the same thing here. All right, it wouldn't have mattered which one of these carbons I chose to draw my double bond with. These are all the exact same, because if I picked one of those structures up and rotated it by 120 degrees, I would have the same thing, right? How if we can like take a molecule and flip it upside down or rotate it and get this other orientation, then they're the same molecule, just drawn a different way. So either one of those, you know, any three of these would have been the same thing. Okay. And then I guess the last thing that we want to be able to do real quick is in our, let me get rid of a bunch of these like scribblings here. Let's pick this first reaction here and tell me what is the nucleophile. You're going to label the nucleophile, the leaving group, and the electrophile. All right, so my nucleophile, that's this thing here. That's what's doing the substituting. My leaving group, that's what I'm swapping out, that chloride. And the electrophile, is this carbon right here. All right, notice that the new bond is formed between the nucleophile and the electrophile. Right, we have our new bond formed between the nucleophile and that carbon that's at the base of our leading group. We call that the electrophile. Okay, the last thing I want to clarify, just because I know it's all, you guys are going to be practicing with your owl. This was an example that Owl gave that if I had sort of spotted it when I was doing the practice and setting it up, I would have warned you guys about, but I totally missed it. This would be something like this, where you have this secondary substrate, but then a weak base, weak nucleophile. All right, and so if we looked at our chart, there should be no reaction for this particular compound. All right, this is like an exception here because this benzene ring is located right next door to that carbon. It turns out that because of that, this forms a really stable carbocation at this position. Secondary carbocations normally don't form, which is why we don't have reaction with weak base, weak nucleophile. But this is an exception when it's right next door to the ring, and so this would actually be an SN1 type reaction. So I'm not going to give this to you on your exam, but again, if you're practicing with your owl, this specific example is going to come up where you have a secondary and a weak base, weak nucleophile, but specifically that secondary carbon is located right next door to the benzene. So if you do come across this specific example, it is an SN1. Again, we don't have to worry about it for the exam, but for practice. Cool. All right. Good luck studying. Send me emails, send me screenshots if you're stuck on something, whatever it may be. All right.